So we are doing mapping the carbon sinks and sources linked to lateral carbon transfers over the globe. So that fits very well within the topic. It's less detailed or more detailed than what you have seen this morning. But at least it's something that is publicly available for use. Those who've seen me before know that I'm an inverse modeler. So you may wonder why I stayed in the world of lateral fluxes, which are a bit different from the atmosphere. And actually, that's because over the years, the comparison of atmospheric inversions with UNFCCC numbers, national inventory reports, has grown in importance a lot. And I would say even unexpectedly, at least to me. If you look at the UNFCCC guidelines, that's the case in the 2006 original text, but also in the refined version of 2019. You see that it seems very simple. There is a section called comparison with atmospheric measurements. And when you go through the section, it starts with inverse models of atmospheric transport. So that's what I'm doing. So that's great. When I read that the first time, I thought that I was really the king of the world, because UNFCCC would just go directly to me. Indeed, an instrument in space like OCO2 is sensitive to the activity of the vegetation, the plants, the trees, the growth of the plants, the growth of vegetable, wood. It's sensitive as well to the fossil fuel emissions of the lorry that will transport the products from a field, from a forest. And it's sensitive as well to some of the activity of the end user, the consumer, that will eat the vegetable and mostly breathe out the carbon that the person has consumed. So it looks great. We have good sensitivity. But actually, when we look at the detail of the UNFCCC guidelines a bit further, we can see that it's not about air-sea fluxes, it's about stock changes. Stock changes and actually at the annual scale. So compared to the cartoon that I showed on the previous slide, the situation has changed a bit. Because it's annual scale, we remove the vegetable, the fruits, we remove the respiration from the end user because it's subannual, so it disappears from the landscape. We still have the emissions from the lorry, but we start to see what is inside the lorry, and with the wood export or import from the forest. So the situation is quite different from what I know from the atmosphere. There are missing terms that we need to have, that we need to compute to compare the atmospheric inversions with the UNFCCC numbers. That was shown very clearly maybe 15 or 20 years ago by Philippe. There is a paper in 2005, 2007, then a few refinements over the years. So we are here with the rest of this talk in the legacy of these ideas, trying to map the lateral fluxes. Our product, we don't have a paper yet, but we have a product. Those are maps that you can just download. If you get the slides, just click on the link over there. We are at version 4.1, so it's a product that is alive. We update it at least once a year. Those are maps of annual fluxes of displaced carbon in unit of grams of carbon per square meter per year. The maps, they cover the period between 1961 and 2022. It's on a bizarre grid of 0.083 degree. You may wonder why it's not 0.1 or 0.01. It's because I used the country mask from the HIDE 3.2 project, and HIDE chose this bizarre grid. So that's what we have currently. We have biofuel fluxes, but they only start in 1990. We make this distinction about the biofuel fluxes only from 1990 onwards. In this map, you have the series of variables with crop use and crop growth, with the distinction possibly with biofuel, and then the same for wood. And then you end up at the bottom of the list with the water terms, the terrestrial biospheric carbon that is reactive to the inland water network, and the surface upward emissions from the lakes and the reservoirs, the lakes, rivers and reservoirs. In these terms, if I come back to my initial motivation, which was the comparison to UNFCCC, you're not interested in all of them when you want to compare inversions with UNFCCC. You're mostly interested in the crop terms without any distinction regarding biofuel. You're interested in the water terms, the last two, and possibly about the general wood terms, if you think that the temporality of the UNFCCC wood numbers is problematic when you want to compare with atmospheric observations. So it's a bit, I would say, compared to my initial motivation, we have done much more than what was needed initially for the comparison. The principle is quite trivial. It's very basic bottom-up approach to map these fluxes. We multiply national activity data with few emission factors. The activity data, they come from national statistics for crop, wood, and energy production. And then once we have the national numbers, we disaggregate them using emitter density maps, human population, animals, or maps of vegetation activity, that's NPP. NPP in crop pixels or in managed pixels of river basins. And then we complete the lot with climatologies for carbon transport through lakes and rivers. So the input to the lakes and rivers and the emissions. In the next few minutes, I will be very boring, but I would like to show you the complexity of what we are doing with the list of the input data. So it's the complexity, but also I would say the fragility, because you will see exposed some of the approximations that we are doing. Because of course, when you will look at the list, some of the input data, you say, come on, in the real world, it's a bit more complicated. So there are a few data that we update every year. So basically, for instance, in 2024, I will have to update the whole database with the updates from FAO, food balances, forestry production and trade, crops and livestock products. Of course, be careful, food balances in FAO, it doesn't mean just food, it also feed and even other uses like cotton, which is obviously not food. We also have statistics from the International Energy Agency, world energy balances and external energy balances. That's for the biofuel. And we end up in the list of input data that are annually updated with the MODIS NPP. So those are activity maps of vegetation activity from the MODIS instrument on board a NASA satellite. And we have an associated land cover type that varies from one year to the next. So that's all what changes from one year to the next. The rest is static. We have country masks, so that's quite trivial. I put that just for exhaustivity. We have masks of managed lands for different frozen years, 1994, 2002, etc. Those are approximations because the national inventory reports in UNFCCC, they report numbers only in managed lands for land use change and forestry, but they don't make the masks public. So we have to make approximations. There is a composition synthesis by Grassi et al. 2023 that we use, and we combine this synthesis with detailed maps for Brazil, Canada, and the US from Ogle et al. From a few years ago. You can see in the middle the map for Canada, where you see that the unmanaged land covers more than half of the Canadian territory in this estimate. Then you have Brazil. You may not spot it very clearly, but you see the growth of managed lands between 1994, 2002, and 2010. You start with the black areas, then you add the gray, and then you add the whitish areas. And then for the US, conterminous US, it's mostly managed. Well, it's nearly all managed. Then a bit in Alaska and non-unmanaged in Hawaii. So those are approximations compared to the NFCCC reports. Forest removal maps, we want to attribute the wood production to the parts of the forest that are actually productive. So it's a bit like managed lands, but it's specific for the forest removal. So those are static. The timing of wood emissions, we use a paper by Earls et al., where you have the temporality of the fraction of carbon remaining in products and landfill. Those are the four curves here. And the x-axis is the number of years after forest clearance. It goes up to 100 years. So we distribute the emissions after the production, the emission to the atmosphere, according to this curve. We have the map of major river basins of the world, so that's quite trivial as well. Gridded population maps of the world for different years. We could also say that it's an approximation because the real world is much more complex. Gridded livestock density maps, so that's for feed, that we combine together using animal standard weights, approximation as well. And then we have static biofuel emission patterns from the PKU CO2 inventory. I'd like to have this evolve from one year to the next because I guess in the real world that's what happened, but the best we have currently comes from this inventory, and we're already happy to have it. And then that's the last slide. Bear with me, please. The last slide for the input data. Dry matter fraction and carbon fraction of dry matter. So those are conversion factors that we take from a paper. But of course, those are frozen conversion factors. The wheat, the carbon content in wheat, for instance, or in maize, is the same whether the crop is produced in Russia or in Canada or in Brazil or wherever around the world. So that's a simplification. We have conversion factors from the IPCC. Those are simple tables that are put in annex to the IPCC documents, maybe a simplification as well. And we have these climatologies of carbon fluxes associated to rivers and lakes from two papers that Ronnie has compiled. There are subtleties. There are subtleties. I will not go through all of them. One of them is the fact that FAO and IEA statistics are not consistent with each other. They have been collected independently from each other, and you can spot inconsistencies. FAO ignores barks and local sources. And we think that they ignore as well primary solid biofuels from crop, but that's not completely sure. I mean, it's not a seamless transition from between the two data sets, and we just the FAO statistics so that we fit the AEA statistics when needed. The other point that I wanted to highlight in this list is the easy double counting. We had to fight a lot with this, in particular with the FAO format that changed over the years, the flag meaning changed over the years. And then suddenly, well, you're fine one year, and then the next year you're not fine, and you find yourself double counting some carbon quantity. This is the full list, but I will not detail it further. After all this introduction, here you have the maps, of course. I mean, those are global maps. You may not see a lot, but just the global pattern. Top left, the crop sink. You recognize the crop location around the world. You can see in the US, the Corn Belt, in Europe, for instance, etc. The crop source, well, it's displaced carbon, so it's more human settlements. You can, in Africa, you can spot Nigeria, a very populated country, the eastern parts of the US, Europe, which is also very populated. India, the southeastern part of Asia. Then for wood, you see forests. For the sink and wood source, it's human settlements as well, but also modulated by the type of activity, the type of heating, for instance, or energy production that is going on in these countries. Same for biofuel. Numbers are a bit lower, but we also have a distribution around the world. Yeah. Lakes and rivers. On the left, the major basins of the world where the NPP comes, when the carbon comes from, and then the emissions from the lakes and the rivers on the right. You can spot the rivers, the main rivers of the world. And if you zoom, you will see less main rivers of the world as well. So this is what we have. This is an example for 2020, but we have the same for all the years. And of course, I mean, my motivation has not changed. I'm excited by these maps, of course, like I hope most of you. But my motivation initially was to have these missing terms when I want to compare my inversions with the NFCCC numbers. I mean, the little stamp on the right are a time series of atmospheric inversions. In blue, you have surface measurements driven inversion. Then in orange, you have something which is driven by the OCO2 satellite. And in red, you have the UNFCCC numbers. That's over the years. Those maps are just here to give you an order of the amplitude of the fluxes that are put together, UNFCCC and inversions. And on the left, you have the correction terms over the years, starting in 1961 up to 2022. The correction terms for three main countries when you want to adjust the inversions to be comparable with the UNFCCC: Canada in green, China in red, and USA in blue. You see that the numbers, and that was also a message from Philippe this morning, the numbers are significant compared to the numbers that you have on the right. It's not something that you can just ignore when you compare the inversions with UNFCCC. They are significant in amplitude, but also they vary from one year to the next. You can see in particular for China, you start from something which is significantly positive, and then you end up with something which is neutral or slightly negative. That's because the trade, the nature of the trade between China and the rest of the world has changed. I guess to feed its own population and to fit its own needs, China exports a bit less or less crop and wood than before, but I haven't digged more into that. Main limitations of these maps. The first problem, I mean, I'm welcoming a suggestion, the uncertainty quantification. I mean, I think we've done together with Philippe, Ronnie, and Yilong good work. We have nice maps. But what is the error bar? I mean, of course, I can throw a number, say 50%, but could we have something a bit better? And of course, the uncertainty depends on the spatial scale. The uncertainty at the national annual scale is smaller than at the grid point scale. But what should we communicate? Another problem, which is minor in comparison to the question of the uncertainty quantification, is the fact that the IEA data that we use for biofuel are not public. And this is something that was put in against us in a paper where we used this map recently. One of the reviewers said, well, you should not use IEA because it's not public. Okay, well, I don't know. That's open for debate. The second problem, the second issue, I would say, is that combining these fluxes, I mean, these maps are beautiful, but if you want to combine them with other maps, for instance, to have prior fluxes for inversions, well, you need to be aware of a number of pitfalls. It's easy to have double counting. I mean, crop, sink, in principle, you have it as well in anything else related to terrestrial biosphere. How do you account for this better estimate? I think that we have. That's open for debate. It's easy to fall into land cover inconsistencies between what we have and what is in the masks used by other sources of fluxes. We don't have subannual variations. Of course, we could impose some of them, for instance, with MODIS, but that's a choice. And last but not the least, we have no coupling with the ocean. We export carbon to the rivers and the lakes. We emit some of it to the atmosphere, but it doesn't end up. We have we have nothing to quantify the exit to the ocean. Still, version 5 is on the way. It's being computed now. With the latest input data from FAO, AEA, and MODIS, it will cover, I mean, it's hidden here by the title, but it will cover the same years, but with better data. And later this year, we will have the data, the estimates for 2023. And with this, I'm done. Thank you very much.